Hello, everyone, and welcome to the session today. Thank you for joining me. Today, I'll be talking about secure infrastructure and a way to speed up development for your developers, a framework that we've used here at Coinbase. I am Adam Link. I am a senior software engineer on the cloud team at Coinbase. But before we get started really too far in our discussion, I want to really narrow what we're talking about today. So what we're going to be talking about is a scenario where a marketing team comes to your infrastructure team and requests that there is a new marketing website that is created for external customers. And the goal here is to help with a new product launch. All right. Now, if your infrastructure team is like my infrastructure team, this is a somewhat fairly common request. And it sounds very simple at the surface, right? But let's dig in a little bit more, because I want you to think about your own company's process for spinning up a new marketing website. If you're like us, it may look something like this. Every website that we have has some sort of a DNS record, which gets resolved to a dotted quad, and that goes to a load balancer. That load balancer then obviously we have in place in the event of traffic spikes, and we use that to connect to some sort of a compute cluster. And the idea behind the compute is that compute is basically facilitating moving files from some sort of a file store system to the load balancer and back out to the customer. And that file store system could be something like an S3 bucket or file store, or just generally on the compute cluster. And then maybe you have some sort of a database, right? And this database is used for the permanent storage of information, like maybe customer email addresses that the marketing team is really interested in getting. And what you'll notice, though, if you're doing the network level architecture, is that there's actually more than just this simple architecture going on. Maybe you're thinking about end-to-end encryption. Maybe you're thinking about encrypting data at rest. Maybe you're thinking about some sort of authentication authorization scheme. And what quickly becomes obvious is that this very simple request from a marketing team is going to require a lot of work on the part of your infrastructure team. So let's go through what some of these things might actually be. So for instance, we're going to start out with some sort of a file system. You need some way to store the HTML files that your development team is sending you to show on the website. You need some way to access those files, some sort of a compute cluster, right? This is going to get the files back to the customers, maybe perform some template and interpolation off of the template files that your developers are sending you. There's going to be a database of some sort for your permanent data store, emails, perhaps other opt-in information or customer information from the marketing team. There's going to be some sort of a proxy, right? And this is important because you're not going to be exposing your compute cluster directly to the internet. You're going to be able to only have the compute accessible through a private subnet perhaps, and you need to now proxy through a public subnet. You're going to have some sort of a load balancer. And this is, again, so you can handle fluctuations in traffic, so you can handle your compute clusters spinning up and spinning down as you do deploys. Perhaps there's some sort of a cache or CDN layer that you're including as well. And this is important if we're trying to serve traffic to worldwide customers, or we care about latency routing, or we want to reduce the amount of traffic that we're actually sending to our compute cluster because we're worried about just showing static pages that are being requested multiple times per second. There may also be some sort of a network configuration. I alluded to public and private subnets before, and we want to make sure that our route tables reflect that, so we're not routing information unnecessarily over public internet where we don't have to. But let's think too about authentication and authorization, right? There may be some sort of permissions to update files. So for instance, maybe your development team should have access to this marketing website, but they should not have access to other websites that your marketing team is working on. Or maybe you don't want to have some sort of back-end API team accidentally making changes to this front-end website. So there has to be permissions around what files can be updated and by whom. Additionally, these files are accessible on the web. And so these files need to have some sort of a cross-origin request sharing or other permissions on the actual files, right? Maybe you don't want your files being accessed by everyone on the internet, and you want to lock down your API requests only to traffic coming from this marketing website. That's definitely something that you have to think about. Also, if you're uploading files, so what type of files can customers upload to your marketing website? Do you even allow uploading files to your marketing website? But on the flip side, what types of files can your developers upload? Perhaps you want to lock down this website to simply HTML files, and you don't want to allow something, like a JavaScript file being uploaded, for instance, in a location it shouldn't be uploaded. Every website has a DNS record, and this is important because you want to ensure that the marketing website you're spinning up for your marketing team is accessible online, and you also want to ensure that your developers can't necessarily change the DNS record at their whim. Network address translation is important, right? Because we have public and private subnets, we want to ensure that we are routing information appropriately. And maybe we have failover routing. If you've worked in the cloud with any sort of cloud vendor for a number of years, you know that occasionally failures do happen, and you want to make sure that you either have an active situation set up, or you maybe have an active passive solution. But in some way, you want to ensure that in the event of hardware failure, that your marketing website stays available. Maybe you're thinking about end-to-end encryption because this is a requirement for your industry, that you have to think about managing TLS certificates and provisioning and rotating keys and encrypting keys. And because this is Datadog Dash, we want to talk about monitoring our infrastructure and monitoring our website. You just built this beautiful website and the marketing team has it up, but you want to ensure that customers can continue to sign up as expected, the website is being delivered as expected, and you want to ensure that if you don't have too many 400s or 500 errors that would show underlying infrastructure issue. There may even be more that your company requires your infrastructure team to provision for this simple marketing website. But here's the bad news. Your team has competition. Your internal infrastructure team has competition from external third parties. Parties like WordPress, who have built a very easy to use plugin and extensible system. Or companies like Wix that provide a easy to use drag and drop UI, or companies like Squarespace that can even include stuff like e-commerce, as well as drag and drop, as well as automatic integration with top mail providers. And perhaps the marketing team wants to send a follow-up email immediately when somebody puts in an email. And compared to these three top tier competitors is your own infrastructure team's convoluted, hard to follow, multi-week approval-laden process. And if you're thinking, well, our internal teams only ever use what infrastructure provides for, there is a problem in the security realm called shadow IT. And this is the point at which your internal processes provide so much friction that teams actually opt for third-party vendors instead of using your internal company's solutions. And shadow IT is a growing and very real problem. If you don't believe me, go ask your security team about it. But at the end of the day, right, what process do your internal teams really want to follow? And for most of us, when a marketing team asks our infrastructure team for help, they really do want to follow our process. But in order to do so, we have to remember that we are competing with third-party vendors. And so we need to make sure we're providing an easy-to-use solution. And this is something that we're going to be talking about in this talk today. So what we want to do as an infrastructure team is productize our offerings. We're going to invest time and effort to abstract away the infrastructure using internal tooling and open source tools. And it's really an investment in your developer productivity and not necessarily busy work for your infrastructure team. You want to think about products that are geared towards your customers' solutions. In this case, as an infrastructure team, your customers are the internal developers and other people at your company. And so when you think about the asks that customers, your internal customers, are making of your team, what are the repetitive asks that you seem to get that you're almost always doing? And then how can you turn this from domain-specific language that your infrastructure team knows into a customer solution-oriented language, right? And we actually struggle with this sometimes at Coinbase, that we think of S3 buckets and other AWS resources, when really what our developers want is a place to store files. And if we can help our internal teams to use our solutions in language that they understand when they just want a website, we can provide a productized website, then your infrastructure team can speed up your developers substantially. And really, engineers shouldn't have to know the underlying cloud service provider that you're using in order to do their jobs well. Lastly, we want to aim for a one-click solution where possible. Now, it's not always possible to do a one-click solution, and we certainly don't have one-click solutions for everything here at Coinbase, but we really are striving to make our internal process as easy, if not easier, than using a third-party vendor. Because remember, we are competing both internally and externally with companies that are focused on quality user experience for our internal customers. So we use the 80-20 rule to ensure that we are productizing the right things. If you remember the book, The Mythical Man Month, in it is described that going from a proof of concept to a product is about a 9x investment in terms of time, hours, and ongoing maintenance. So when we do productize an offering instead of creating a one-off solution, we want to ensure that we are adequately getting the return on our investment as an infrastructure team and making sure that we're not overly productizing one-off requests, because those can just be a proof of concept. So let's talk about how we did this here at Coinbase. So when I go through the next few slides here, you'll see our Coinbase logo, and this is an internal tool that we've built and maintain. Right? So this may not always apply to your company, but we'll talk about a broader framework that may apply to your company right after I go through these tools. So the 4 tools that we use are GitHub, GeoNodes, which is an internal tool we built, GeoEngineer, which is also an internal tool that we built, and Terraform, which is the open source API and just general cloud provider declarative framework that I'm sure everyone is familiar with. Let's go through each of these tools in turn. So GitHub is where we codify our infrastructure. And this is a version controlled way of keeping track of what should be running in our environments. Our GitHub is consensus based. What we mean by this is that any change that happens has to have at least 2 people who are not the code authors agree that the change being made is good and approve it. We also have what's called the declarative state of our infrastructure in GitHub. And this is a result of the fact that we use a declarative way of templating our cloud infrastructure, but it's very easy to see what is running and what should be running in various environments. GeoNodes is something I'll reference quite a bit, and GeoNodes is essentially a YAML template. So it's an abstraction that we built into YAML, and this is the product that we as an infrastructure team provide to our internal developer customers. It is a interpolation and has YAML flexibility built into it. So what I mean by this is we provide for interpolation of some environment variables inside the YAML, and we'll get to how we do that in a second. But we also have native YAML flexibility, such as YAML anchors, that can be used so you don't have to repeat your codification. GeoNodes are also not meant for complex loops or logic. And the idea behind this is we want our developers to focus on declaring the infrastructure they need, not necessarily programming the infrastructure that needs to be created. We also have extensibility options built into our GeoNodes. So for instance, we have easy ways of adding like lists of tags or extending out some Terraform features that we don't necessarily have to codify, but we just get for free. GeoEngineer is really our codification tool that we use. And this is the logic layer behind everything that we do as an infrastructure team. And this is really where we translate the YAML from YAML that our customers see into a declarative state file that Terraform is able to run. And we do this by adding additional things like logic and security defaults at the GeoEngineer layer. And this is where we have wrapped the Terraform planning and apply engine with our own CLI tool. And this allows us to then use the GeoEngineer logic layer throughout our infrastructure where we need it. The other cool thing, and I'll get into this later, but the other really cool thing about GeoEngineer is automatic validation. So we're able to kick out a infrastructure change set that we know will fail when it gets built in the cloud automatically. And we can do that before we even begin building cloud resources, which helps developers get feedback faster about the infrastructure that they want to build. Lastly, we have Terraform. And Terraform is our low-level state file generation tool that allows for enumeration of resources and interacts with the Cloud API. In our case, it's Amazon Web Services, but Terraform also allows interaction with providers of all sorts, not just cloud tools. So you can even do things like codify Datadog, codify PagerDuty, and loop in other tooling that your infrastructure team may use. Terraform also does our planning and applying. So we use the open source version of Terraform for plans and applies, much the same that many in the open source community do use. So the result of these 4 tools gets us to this very cool productized solution. 6 lines of YAML. And these 6 lines of YAML allow developers to spin up a new website, in this case, the newproduct.com, and all they have to do is upload their files and the website is live. So what's really cool about this is what do developers get for free with these 6 lines of code, right? Why did we even do all this? Well, we did this because this is what developers get for free with our tools, right? And this is what we provide to our developers because everything except for database and DNS comes along with the notion of geoengineer, automatically adding sensible security defaults and adding additional resources as needed to successfully deploy a marketing website. We don't have databases or DNS records by default because databases are codified through our geo nodes slightly separately, and DNS is also codified, but we do that through a slightly different process. Let's do a deep dive into these tools, all right? So before we do a deep dive, there is one more tool that we use internally that we wrote, which is our continuous deployment engine. This is our internal tool that we have talked about before, but it is not open source. You can easily replicate what our continuous deployment engine is doing by using other tools like Travis, Jenkins, CircleCI, or even Spinnaker. So the way all of our tools work together is the GeoNode YAML gets checked into GitHub, at which point our consensus engine that we call Heimdall, and we've written about Heimdall before, basically this is just making sure that other developers agree, and it just blocks the git pull until everyone agrees that this change is acceptable. And then once a change is acceptable and has appropriate approval, that change is then merged in automatically, at which point our continuous deployment engine takes over and begins applying the changes written in the GeoNode YAML through our geoengineer apply engine. So here you can actually see the GeoNode YAML as it gets translated into a geoengineer object. For those that are familiar with multiple languages, you can see here that geoengineer is written in Ruby. And so what we're basically doing is we're taking a YAML file and translating it into a Ruby object to begin manipulating the object. And so the YAML on the left-hand side here is what our developers see and the ease of which they have to access all of this underlying complex logic. So once we have a geoengineer object, we can begin to check for attribute validation. And these attributes are checked not only that the required fields exist, so for instance, we make sure our developers fill out the bare minimum needed to deploy a new resource to the cloud, but we can also check the attributes for syntactical validity as well as logical validity. So if you're familiar with like AWS S3 buckets, there is a regex naming scheme that must be fulfilled in order for the bucket to be successfully created. So we can check for this automatically on our geoengineer side and kick back a bucket that we know will fail when it gets built. Likewise, we can check for logical validity in terms of making sure that traffic going over port 443 is encrypted, or that traffic going over port 80 is not encrypted, and other logical validity that we can check for. We also set security defaults in geoengineer. And so you can see here that what we're doing is we're applying a JSON policy to an S3 bucket by creating a custom policy for the bucket, as well as attaching a generic read policy. And these two get combined together and then automatically attached into the S3 bucket before it's created. In this way, we can guarantee there's a layer of security around that S3 bucket, even if our developers never write that layer of security in. In fact, we prefer that they don't because we can control the sensible defaults for security by default. We also can do things like include metadata in tagging of resources. So for instance, based on the file structure of the GeoNode YAML files, we know what team owns what resource, and we can automatically tag the resources before they're created with the owning team's information. This is incredibly helpful when it comes to billing and attribution to understand who's using what in your cloud environment. We also make use of metaprogramming inside of geoengineer. This allows us to define what we want to create and then use metaprogramming to actually execute the function. So in this case, you can see that we're creating 3 different resources: a bucket, an identity, and a distribution. And this create underscore method is actually a magic method that we can define what that function is going to do through metaprogramming, and then automatically return back objects to our geoengineer node, and then set up and add the security through these setup underscore functions. So it becomes very easy to create a framework to bring new resources in as our cloud vendor adds them and as Terraform adds them, without adding additional code and additional overhead for our team. Right? So really, we can use a don't repeat yourself mentality when it comes to codifying resources and providing products to our internal developers. We also have full YAML extensibility. And so what you can see here is both interpolation based on environment context variables, as well as YAML anchors. So we're defining a static image bucket in both development and production, but we're doing that using a YAML anchor and then allowing the bucket name to be dynamically named depending on the environment in which we're executing geoengineer. So this makes it very easy for teams to spin up identical production and development environments where needed, and ensure that we don't have bugs being introduced in environments simply because we've codified infrastructure slightly differently. This also applies to Datadog. So every new account that we create in our cloud service provider in AWS, we can automatically bring in Datadog through GeoNodes using GeoEngineer to automatically create roles. And then we automatically provide policies that allow those roles to be assumed by Datadog. And then we very quickly have the ability to monitor our infrastructure, even going so far as to monitor our dashboards in Datadog to detect drift based on what should be codified. We also allow our developers to instantly get log output from Lambda as well as other long-running processes by automatically bootstrapping that in to new accounts using GeoEngineer. So let's go ahead and let's actually try this at home, because this is the most important part, I think, of the talk. For everyone else is how can you take what we've done at Coinbase and apply it to your own company? So before we get into why that's cool, let's start with why even bother with this. Right? There's going to be pushback because creating these tools and using them is an investment in time. And it's really, one pushback you get is it's abstractions on top of an API on top of hardware. And that's true. But this also follows to the second, objection of, well, Terraform and other modules and other declarative languages provide a lot of this already today. And that is somewhat the case. But certain things like Terraform modules don't also have the logical validity checking that you can have with an internally built tool. They also don't allow you to easily codify your business rules. And so we can codify business rules inside of GeoEngineer. The last thing is it's expensive to build and maintain internal tooling like this. It may not make sense for smaller engineering teams. You may want to look at open source tooling. But for larger engineering teams, especially larger infrastructure teams, investing in these tools can help your developers speed up. And I'd like to ask just some philosophical software questions now in an attempt to answer why even bother to do this, right? And one of the questions is, why do we separate the data layer from the application? Right? And why do we separate business rules from the data store layer? And why do we separate the application logic and build it on top of data manipulation languages? Why don't we just send values to SQL and call that good enough? Well, the answer is because by breaking dependencies, we can speed up development and increase security. And because infrastructure is now so codified, you can break the dependency on your infrastructure team and your underlying infrastructure in the same way that you've broken dependencies in your application. And this allows you to speed up your developers and increase security. In fact, what we're doing by breaking this dependency is solving this chart. Right now, if you have an infrastructure team that is depended on for your deploys and must work with your developers, as you scale your development team, you must scale your infrastructure team. Otherwise, the infrastructure team becomes the bottleneck. But with a self-service productized offering to your internal developers, this is what you can do with your infrastructure team. As your developers grow, your infrastructure team now grows at a less constant rate. And the objective here is to eventually plateau your infrastructure team in a way that allows you to leverage the tooling that your infrastructure team is building to serve more developers instead of directly adding headcount to meet the increased developer demands. So what we're essentially doing is a dependency inversion, right? Developers don't really care how they get a website. They just want a website. Infrastructure doesn't really care what they're running as long as it scales and scales well. And your security team doesn't really care what it does, just so long as whatever it is being done securely. We've accomplished this dependency inversion through our GeoNodes and GeoEngineer by providing interfaces to the underlying hardware that our developers can consume. And in this way, our infrastructure team can invert the dependency on our human hours and provide these abstractions to our developers, which allow our developers to do their job and allows us to focus on our internal tooling. So the framework is really 5 layers. At the very top layer is this single line implementation. This is the holy grail and certainly something that we are striving towards internally at Coinbase. But the objective is to make it as easy as possible for your internal customers to use the products you create. Underneath that is a layer of technical and security abstractions and additions. And this is where your infrastructure team can build tooling on top of that one-line implementation to bring in sensible security defaults. You then have a declarative language that gets generated at the next layer, which is consumed by your API layer. And this is where you are now beginning to interact with hardware resources or perhaps your cloud vendor. In order to do this, you have to start at the bottom and build upward. In order to get to that single line implementation, you have to have everything else in place. So at Coinbase, what we do is we have our single line implementation through our GeoNode YAML. We then add security and technical logic through GeoEngineer, which is, again, one of our internal tools. We have the declarative language provided by both GeoEngineer and Terraform, which then gets fed into Terraform for planning and applying in our cloud environment on AWS. So for your own company, step 1 is to look at finding a cloud vendor, or you can do this on-premise with VMware and other virtualization tools. The next step is deciding on an API layer. We chose Terraform because Terraform works with multiple providers, not just AWS, and allows us to codify additional components of our infrastructure that we care about as an infrastructure team. But perhaps your company is okay with building directly on top of one of the products provided by one of the major cloud providers, right? Like CloudFormation. The third step to do this at your own company is to identify common use cases for application types. And what I mean by this is really thinking critically about what your infrastructure team is asked to build. So for instance, are you constantly asked to build short-lived function calls, where something like a serverless application may be a productized offering you can offer to developers? Do you always have long-running Docker containers that need to be built? In which case, can you build a product to offer your internal developers that provides the infrastructure to run a Docker container? At Coinbase, we have blockchain nodes. We are a blockchain company, and there's a particular set of hardware and software requirements to run blockchain nodes across multiple different types of blockchains. And this was a common use case that we, as an infrastructure team, were asked for, and we have built a productized solution internally at Coinbase that makes it very easy to provide new blockchain nodes. Perhaps you're a data company and you need some sort of ETL process that you're constantly asked for, and this could be a productized offering your infrastructure team could provide to your data teams. Or maybe there are functional requirements. If you remember back to our marketing website that we started with, if this is a common request that you get, then perhaps you can productize a marketing website and offer it to your internal developers and marketing team on behalf of your infrastructure team. You should also work with your security team to determine what sensible defaults to include. For instance, we include encryption everywhere. And this is really end-to-end encryption and encryption at rest. And we build this into our tools by default. So any new resources that are created are automatically encrypted everywhere. And this buttresses with TLS, automated certificate provisioning. Because our developers don't have to even think about TLS certificates, we just handle it through our productized offerings. Maybe you need to think about identity and access management. We certainly use common authentication and authorization, but maybe your security team says, we only want these resources to be accessed by certain IP addresses. Can your infrastructure team productize that into your offering so your developers don't have to think about it? Or maybe you want to think about automated integration into internal tools, right? So maybe you have a CI/CD process that you can automatically integrate into, or monitoring, or alerting, or PagerDuty. Or maybe you want to think about automated integration of testing and monitoring, or automated deployments, or automated builds, or automated static code analysis for security vulnerabilities. You can productize all of this by providing a simple interface to your internal developers, and your infrastructure team can now manage these tools instead of having to run security tests to ensure that code is functional and secure. Or maybe you have other industry requirements. HIPAA, for instance, FINRA, financial regulations, right? Maybe there are things your security team needs to know are codified in your infrastructure, and you can just provide this to your customers. And in that way, your security team can sleep better at night, and your infrastructure team now knows that your developers are only spinning up resources in compliance with industry regulations. And lastly, the tool you want to think about is what open source tool can you leverage? We've open sourced GeoEngineer a while ago, and since then other tools have come along. Terraform and TerraGrunt is a great example that you can use to use modules as a way to productize your infrastructure, or even something like AWS's Cloud Development Kit, where your developers can help themselves and codify resources. Where this has all come together for us is 4 of our values on the engineering team, specifically on the infrastructure team. Our first value is security first, and we've been able to achieve this goal by productizing an easy-to-use interface upon which we then build sensible security defaults such as encryption everywhere. So we know that security is automatically baked in at the infrastructure layer to our products. The next value that we have is 1, 2, automate. And this basically says that by the 3rd time you're doing something, you should really think about automating or productizing. And for our common asks, we've productized our offerings for our developers. And in this way, we've automated the work. We are also API driven at Coinbase. And this is important because by providing an API abstraction layer, both at GeoEngineer and our other tools, we can run GeoEngineer locally on workstations or in our continuous deployment pipeline. And lastly, the value of building value. We build value as an infrastructure team for our internal customers and speed up their development by productizing our internal tools, by productizing our offerings, and by allowing people to spin up infrastructure but not have to worry about the underlying hardware or how it all fits together. And in that way, our infrastructure team has built secure infrastructure that speeds up our developers. That's all that I have today. Thank you very much for listening. I'll be around to answer any questions you may have. Thanks.